Before I introduce our distinguished keynote speaker, I wanted to wrap up my introduction by setting the stage. The Earth to Sun distance, as most of us know, is about 93 million miles. With apologies to my European visitors, I speak in miles when I'm in the US. When I'm at work, I tend to think metric, but when I'm not in the office, for some reason my brain switches and I'm suddenly thinking in feet and inches. So you'll have to stick with me on this. The Earth-Sun distance is about 93 million miles, which is such a huge distance that for convenience, astronomers shrink this to 1 astronomical unit. Well, for purposes of illustration today, I'm shrinking this to 1 foot to make a point as we work here today. So if you consider the Earth to Sun distance to be about 1 foot, then the Pluto to Sun distance, just approximately, given that it's in an elliptical orbit and it's rather eccentric, is about 38 feet away, okay? 38 times 93 million miles, 38 astronomical units, or roughly the size of this auditorium toward the back is the distance from the Sun to Pluto. On this same scale, to get to the nearest star, we have to go halfway to Nashville. Okay? That's the challenge we face here today. It's an enormous challenge, going from a few AU to 271,000 AU, or going from a few feet to about 51 miles. So just keep that in mind as you're hearing the presentations today. We have a daunting challenge, so let's get started and let's make it happen. I have the distinguished pleasure this morning of introducing a Huntsvillian who has flown in space several times on the space shuttle. She is no stranger to those of us in Huntsville, and if you drive through Research Park, I don't know how she feels about having a road named in honor of her, but I passed by it many times coming in to Huntsville. She is going to talk to us today about human spaceflight and some of the challenges posed for flying humans in space. The relevance of this to the Interstellar Workshop is that the dream we all have is not just sending, at least I think we all have, is the dream of not just sending robotic probes to the stars, but one day taking us as a species. And we need to kind of level set on that, I think, because the challenges that we're going to have with sending a robotic probe, 271,000 astronomical units, pale in comparison to what it'll be like to send humans. And so Jan is going to give us some insight today from her experiences flying in space and what some of the issues are associated with human space flight. So Dr. Jan Davis, thank you, Jan.
Thank you, Les, and thank you for inviting me here today. I don't have any really neat music playing, and I don't have any, sexy rocket ships to show you. And I did have some slides from Hubble and Chandra in the background of my slides, so hopefully they'll show up. But there is a galaxy up here if you can't see it, and there's a little dot that says you are here. So what I'm going to talk about today is some of the challenges of flying people in space, our needs, our adaptation to Earth and what that entails in terms of problems going in long distances or long duration flights, and then also some reasons you want to send humans into space. And how long do I have left before?
You're going to have up to 45 minutes.
Okay.
We'll give our keynote.
I don't want to get the hook. Okay, so to first talk about some of the challenges, environmental control and life support with emphasis on life is one of the biggest challenges. Also, we need to eat, we need to drink water, we need to get rid of that. There's hygiene involved, storage for a lot of different things that we need. The medical effects of low or zero gravity, by the time you go interstellar, you'd be in zero, but right where I was flying, we were still in microgravity, feeling the effects of the Earth's gravity. And then socialization, how you deal with that. Hobbies, culture, even though you have the theory of relativity and people can debate what time does and those distances, you still have that issue of people's longevity. The psychological effects, would it be a one-way trip? And if it's a one-way trip, what does that involve? And then the maintenance of the spacecraft can be a challenge and an opportunity for humans. And then emergencies, what if something happens? What do you do? And I'm really sorry you can't see my cool Hubble picture. I should have made it brighter. So a lot of people think about, well, what is it like to fly in space on a space station? And this was on a Family Feud game show, and so you can see the perception of what it would be like, if you're even just on the space shuttle or space station, which is in low Earth orbit. Bad food, lonely, no gravity, no bathroom. Actually, they do have a bathroom. No fresh air, cramped. It's cold. It's cold or hot, depending. But anyway, just people's perception of what it would like to be in space is not generally a good one. As far as the life support part, we're already doing a lot of this breakthrough technology on the International Space Station, where we're turning urine into drinking water. And we're even getting it with the Sabatier, we're even able to get rid of the CO2 without carrying LiO canisters or something like that. So this is a mock-up, but on the space station there are 3 separate racks. That's how much weight and volume it took to do this revitalization of the water and the absorption of the CO2 and turning it into something you could dump overboard. So we have the technology. It's not been used on the Earth because, if you use submarines or bunkers in the White House or whatever, you can usually resurface or get more supplies if you need to. Whereas on this technology in the space station, it's totally closed loop, which is a really nice feature. There's temperature control. We have both on the space station, active and passive, but you fly interstellar or even within our own solar system, you have to have that thermal control of even our probes that we have that are going interplanetary. And then water production, which our closed loop system does. Water is very heavy. It's about 6 pounds a gallon. And so if you carry the amount of water that people require, it's quite heavy. So you really need some sort of closed loop system to generate that water. We do have to eat. And as you can see on the International Space Station up there, it's quite a social event as well. And you can see bags of liquid. We use a lot of water to rehydrate food and just for our own, health of drinking water. But also we use it a lot for rehydrating food, because if you carry food that's hydrated, of course that water mass adds a lot to the weight of the food and the storage size. And so most of what we carry is rehydrated, and it's not bad. And then over here, you can see that we do carry some fresh food on the shuttle and station, but it's of limited duration, so you have to eat it up pretty quickly. So most of it's freeze-dried, and so you have to have water again to rehydrate. Of course, getting rid of that is kind of tricky. We talked about the closed-loop system for urine, but there's another byproduct that we produce that's a little more difficult to get rid of. This is the WCS waste collection system on the shuttle. It's similar on the station, not even quite as nice as this one, where we actually, with the number 2 stuff, we actually have we call it a slinger. I don't know what the official name is, but it's a spinner that spins it, and so it's on the outer wall of this drum, and then we expose that to vacuum and it crystallizes. And so that's how we get rid of it. We don't dump it overboard though, but it does get rid of some of the liquid and the mass and the other byproducts. So that'd be something you'd have to deal with. Apollo, Mercury, we had small volume, Gemini, but they kept all that stuff in bags. So, you can't really do that for a long period of time. And contingency, what happens if that doesn't work? You may remember on the space shuttle, the first few flights, we had some problems with this WCS. So we do have backup capability, bags on the shuttle and station, but it's not something you'd want to do for very long. We have to have hygiene, or it's a big problem if you're traveling with more than one person. The upper left is Pete Conrad on the Skylab. We actually had a shower where they would squirt water on and then vacuum it off, because it's just the surface tension that keeps it on your skin. There's no gravity for it to drip off. And then you're brushing your teeth. All these other things you do on the shuttle and the station. We don't have a shower. We just used a water hose, and we had shampoo that you didn't wash out of your hair, and you just take sponge baths basically. For brushing your teeth, we just swallow the toothpaste. So it's just regular old toothpaste, and we swallow it because we, sink doesn't work for one thing, but there's really no place to put the fluid of that. So those are all things to consider. Sleeping quarters are pretty easy because you can just kind of hang out anywhere you want, but we had sleeping bags and would strap ourselves somewhere. And also involved with flying humans are the volume of clothes and all kinds of stuff that we need. So those things take up space. That's me brushing my hair, all those hygiene things you have to take with you, your clothes, whatever else you need. And this lower picture is the multipurpose logistics module, which is what we use to carry these types of things to and from the space station. And so you can see these lockers of supplies. Now, some of them are experiments and things like that, but most of them are food, clothes, expendable things that we need, and things that are brought back on the Progress, which we use now on the International Space Station. Those burn up in the atmosphere, so we don't even bring those back. But in the MPLM, we could bring things back. So it's an interesting problem if you think about, those things that you need. How do you get them up there, and then how do you get rid of them when you don't need them? And I thought this was interesting, and it was kind of fun for me to read about interstellar travel, because it's nothing I really, planned on how humans could do that. But someone had this analogy in the literature that I read that the Mercury capsule, when it flew with a person on board, had 6 times the mass and volume of a Sputnik satellite. So if you use that kind of as a rule of thumb, I don't know if it's a good rule of thumb or not, but I thought it was interesting. Just take a 6 multiplier for anything that you want to fly, like in an interstellar fashion, or it may even be more than that because of some of these other issues I've talked about. So it does take more volume and space and mass and all these other things I talked about to fly humans into space. Bone and muscle loss is a big problem for us. We're adapted to Earth, we're adapted to gravity. When you fly in space, even just for a short while, my longest flight was 2 weeks, 12 days in duration. And so I didn't really lose that much bone and muscle, and when you come back to Earth, you get it back. People, as you see here, who come back from flying on the International Space Station, they're not allowed to stand up or use their bones and muscles for fear they might damage something because they have lost so much bone and muscle. And there are ways to help that reduction. But people who've flown 6 months to a year, sometimes the effect is permanent. And so you can imagine if you have to fly more than a year, then it could really be a problem. Now, there are ways, as I said, to get around that, but they only help the reduction. They don't get rid of the reduction. And then when you come back to gravity, most of it comes back, but for some people it doesn't come back completely. The radiation effects, I'm part of a longitudinal study. All the astronauts go back to Houston for their physical every year, where they study the long-term effects of spaceflight. And the 2 things that are outside of the normal population for astronauts are cataracts and cancer. And so I'm a living example of the cataracts. I had one replaced 2 weeks ago, and I have the second one tomorrow. So I have cataracts. All 3 of my flights were high inclination, so I had the higher radiation, and it's affected my eyes. Hopefully the cancer won't come, but these people who are up there 6 months or longer, their radiation is very closely monitored, and it limits how long they can fly. Some of the astronauts have been told you can't fly again because you're at your radiation limit. And so that is a problem, and we're just, above the Earth's atmosphere. That's the Aurora Australis, by the way. It's beautiful. You can't picture it on film. It's just absolutely gorgeous. As I said, the bone and muscle loss is one thing, and we try to help that by exercising, but it's hard. You have to put tension on yourself to exercise, whether it's on a bicycle or ergometer like this one. We've tried different things. There are lower body negative pressure devices, the penguin suit that the Russians use, a lot of ways to try to help that. But your heart doesn't have to work as hard because it's not pumping, you don't have to recirculate everything in your extremities, because with gravity, the heart has to fight gravity, so it has to work harder to get that fluid back. But without gravity, it doesn't have to work as hard. And that's really why they exercise, more so than the muscle and bone loss, is to keep the heart active, to keep that aerobic activity. We were required to exercise an hour a day, and on space station, it's anywhere from 2 to 4 hours a day to try to help those things, those medical effects. And then socialization. The upper left is my daughter, which is family, and that's one reason I put her up there, but the dog is really the main reason I put it up there, because when you're in space, you hear a lot of people. You can hear voices, but you don't hear the normal sounds of Earth, like dogs. And you hear about a cat or a dog tape being sent to an astronaut, and that's why, because you just miss those, sort of those natural things you hear on Earth and take for granted. The center picture is my husband and I, and again, the reason I put that up there was not only because of him, but because of the ocean behind us. The sound of waves and the wind, just the feeling of wind is something you don't feel in space and that you really miss. Likewise, snow and just, running water, all those kinds of things are things that we take for granted, but if you're used to hearing them, it's something you really, really miss when you're up there, even for a short period of time. The effects of isolation. On International Space Station, of course, people aren't isolated, although I flew with a Russian guy who had been isolated for 10 months. And that was, well, not the whole 10 months, but a good majority of the 10 months. And you heard about the Russian who was stranded when the Soviet Union collapsed. That was him. But he said that really being in space up to 6 months is kind of fun, but longer than 6 months is really not so much fun. And so we've done studies of isolation on astronauts. The underwater lab is one way. We've sent astronauts there. Not only are you isolated, but you're in a harsh environment, which is the same as in space. So there's a psychological thing there that we're studying. And then Antarctica is the other one. We have astronauts who spend time on Antarctica, in these isolation studies and these sort of harsh environment studies, very similar to being in space, where you have limited resources, limited communication, harsh environment, dangerous environment. You'd die if you got outside of your vehicle, those kinds of things, which are what we have in space. So that's a problem for us, and something to think about. We have hobbies. If we've lived on Earth any amount of time, we develop hobbies. People play musical instruments, they read books. We have holidays like Christmas that we celebrate on board. A lot of times the astronauts are on board during holidays, and so they celebrate, and the ground tries to help them celebrate, because that's part of their culture, part of their upbringing on the Earth. And then, if you thought about 50 or 100 years or however long it would take, how is that going to work with our longevity and also the psychological effects? If people, and I know people would sign up for a one-way trip, but that's still something, once they got up there, they may not think that was such a good idea. So, how do you deal with that? One of the challenges is, and that's Chandra up there, which is outside of an orbit where we can maintain it with people, with extravehicular activity. But if you send something interstellar, or even the ones we have interplanetary, they have to have enough redundancy where you don't have to do maintenance on them. And if you had an astronaut on board, you'll see in my opportunities, that's one way to handle it. But also, if you have an astronaut on board, you want to be on something that's pretty reliable. We have problems now on the International Space Station because we don't have a large vehicle for these large spare parts. And so we have 3 different ways to get things up to space station, but we really don't have a way if something major broke. So they while we were still flying shuttle, they took up these big spares and sort of staged them on the station so that, you know, if something happens to one of those critical large items, like the control moment gyro or something like that, you know, they'd have it right there. Well, if you're going interstellar and you have a problem and you don't have the spare parts and, you know, those kinds of things, that can be an issue. If you have people on board and you have an emergency, what are you going to do? Now, if somebody signed up for a one-way trip and they got sick and were going to die, well, I guess that's part of the hazard, just like when people came to explore and go across the sea to America, you know, a lot of people died, and that was just part of the risk of going. But if you're going to try to save somebody, there are ways. I mean, on 2 of my flights, I was a medical officer where I trained how to pull teeth or do CPR. We had some special straps we could do CPR on someone, and this is Ray said, and she's a medical doctor. She helped develop those straps. She's in the Vomit Comet trying to see if it'll work. So there are some things you can do to stabilize somebody. Now, our goal on Space Shuttle, and I think it's the same for Space Station, is to keep that person stable and get them back to Earth in 24 hours. And so, you know, I wasn't going to do a heart transplant or something like that, but I could do a tracheotomy, and they taught us how to do that. So, you know, if you were on a long space trip, what would you do if you had a major problem? Now, the other thing we do is we screen people before they fly, so you have these healthy people, and so they're not going to have a chronic problem. So hopefully that helps, and that would help if you were doing a long mission as well. So on the positive side, people have this amazing capability that you can't do with robotic probes, to discern and judge and make decisions and learn, give you feedback, you know, talk to the scientists, change things, those kinds of things. We have mobility. We can move around and look at this or look at that or go here, go there, and respond to commands. We can communicate, you know, not just listen and do what you say, but talk back and have that feedback loop. And then we can maintain spacecraft. We do it all the time, and so we've got the capability to do that and the technology with the suits and that kind of thing to maintain the spacecraft. So the bottom right, you know, I'm in the training module here. It actually was in Huntsville for my Space Lab flight, and so, you know, with people, we trained with the scientists, we trained with people who design the equipment and people who design the software and that kind of thing. So we understood how things worked, and we understood how the science was supposed to work. And so, you know, we could be trained on that, and we could be the eyes, ears, and hands of the scientists, or whatever we needed to do. If we had a problem with one of the racks, we fixed it the first day. It was with the cooling loop, so if that hadn't been fixed, we would have lost a lot of the experiments. Looking out the window with a Linhof camera, I, you know, see something interesting and I'll take a picture of it. Or, you know, we get briefed by the Earth OBS scientists, if, you know, this is going on the Earth, we want you to take a picture of it. So there's that interaction and feedback that humans can see something and process it and make a decision or change something, which, you know, if we were on Mars instead of the robotic landers, which, by the way, I think the robotic part is absolutely essential to space travel, and I'm not saying you shouldn't do it. I'm just saying I think it's good to have both, because humans, you know, can make decisions and decide what they're going to go do and go get, like they did on the moon when we got the rocks on the moon. Those folks had worked with the geologists, so it's just another dimension from the robotic probes, but definitely you need both. Mobility, this is inside part of the Russian part of the International Space Station. And, you know, that space station, we can get around and move and do things and fix things and, you know, get things and do whatever's needed to carry on the mission. Respond to commands, as I said. The upper left is the International Space Station, and it's the robotic workstation where, you know, we can do things in response to what needs to be done or what someone tells us to do. Bottom right, that's on my Space Lab mission, where we had a lot of materials experiments and furnaces and things like that. And so it was a dynamic environment where we had to respond to how things change in microgravity versus, you know, the way we were trained on Earth. Or we spent a lot of time discussing things with the principal investigators on how an experiment we might want to change it for the next run. And we can communicate. This picture is from my second flight, where we were trying to grow a crystal of insulin. And we, of course, this was a one-shift mission where everybody went to sleep at the same time, and we had a strict timeline when we were supposed to go to sleep. And I was supposed to go to sleep, but this crystal started growing. And when it starts growing, you have to change some parameters on the equipment and monitor things in a different way and, you know, be in the loop, sort of, to make sure that it keeps growing. And they wanted me to go to sleep, and I said, no, I can't go to sleep. We're growing this crystal of insulin. And so that interaction and that intervention by me and the work with the ground, we were able to grow that crystal of insulin. Back in '94, they didn't know what insulin looked like, if you can believe that. They had 3 candidate structures for it. And with this crystal that was grown, it was a perfect crystal of insulin, and they were able to determine the structure of insulin, which to me, this is one of my proudest moments. But it does show, you know, with people in the loop, how things can be dramatically different than if it's done just automatically. And I said, we can maintain spacecraft. We can do extravehicular activity, although those suits weigh a lot, and there's a lot of overhead, and supplying those suits with oxygen and, you know, CO2 scrubbers and water loops to cool us and all that, that's a big weight hit, but we can maintain our spacecraft with them. Even interior, we have to maintain a lot of things on the space station. We did on the shuttle too. So that's a big plus in having people on board, is that they have that capability to maintain the spacecraft. Just some alternatives. I know you've probably thought of these. You probably thought of more than I have, but we absolutely have to combine robotic probes and humans. You know, maybe have a human base and robotics, send a robotic somewhere would be another alternative. But having humans go all the way out as far as Les was talking about, interstellar. Remote bases. We've seen that in a lot of the science fiction type literature. We might have to induce gravity, because if you take humans who are adapted to Earth, they're going to need some kind of gravity in order to maintain their health. Progeneration of humans. If you do that, you know, how are you going to train these children, and how are you going to, what kind of environment are they going to grow up in without any gravity? How would their bodies develop? And then suspend life. You hear a lot about that, you know, cryogenically, or, you know, induce people to hibernate so that they can take these long trips. So we do have a robot astronaut on board the space station. You may have heard about that, the Robonaut. And the Robonaut and the astronaut there on the right. The Robonaut can do some very intricate things. It's really pretty amazing. And so there are a lot of ways you can use something like that instead of a human to carry out your mission, but you still have to program it, direct it, monitor it, and you know, make sure it does what you think it's supposed to do. Remote bases, it was kind of fun to look at different concepts for these remote bases. Of course, the lower right, you see a lot of where it's turning so that you can induce gravity. It's interesting, a lot of the remote base pictures I saw had the Earth just, it looked like they were in low Earth orbit. I'm like, You know, you really don't need to do that in low Earth orbit. But if you go way away from low Earth orbit, you really do need some sort of base that you can launch from to go wherever it is you need to go. And one in the middle I thought was really interesting. It's like a whole village and plants and everything inside of something, a toroid, sort of like on the right, where you have the gravity as well. So humans, we're adapted to Earth, and so we're not really suited for long periods of time and space. So, you know, we'll have to do something about that. And I really believe that the best mission you can have and the most you can get for what you need to do in your mission can be obtained by having humans on board. We, of course, present these challenges I talked about for very long duration missions, but we can also add a lot of things to the mission that you wouldn't be able to get any other way. We're just a very specialized, highly intelligent, highly sophisticated brain that, you know, can do things that we've not been able to find a machine, or although people are working on that, artificial intelligence, but we have other capabilities as well. So we need something to cut down the travel time, and I've read about some things people have thought of to get us there more quickly, but the propulsion part is, or maybe not even propulsion, maybe, you know, like the transporter, like they had on Star Trek, something like that would be needed. So it takes about, to train an astronaut, it takes, to get educated through college, and minimum of 5 years of training. So, you know, you're looking at about 30 years old would be the minimum age for somebody you could launch into space. So unless you can compress that somehow, you know, you're looking at 30 years old. So, you know, 30 plus 50 or 30 plus however many years, we've got some challenges to cut that time down, that travel time down, so that, you know, we as humans can go those long distances for those long periods of time. So I'm glad people like you are thinking about it and trying to figure it out and making it happen. I just think it'd be really cool to be able to do that. Well, that one came out. Okay, that one I didn't ghost. That's why it came out. But anyway, I'd be happy to answer any questions. I don't know how much time I have left. Looks like maybe.
You have time for questions if you
okay.
have some. So.
All right. Yeah.
I was wondering, has there ever been any studies done to see how much gravity is required to mitigate the long-term effects? Would having a colony on the moon provide enough gravity to mitigate those effects, or would you need more?
Well, I don't know of any studies like that. I know we were, with the Constellation program, that was our goal, was to have people in the 1/6 gravity of the moon for 6 months or longer to see how we could live and work on a remote place. But, you know, microgravity in the low Earth orbit is just that. It's about 10 to the -6, which is not enough. So I don't know that they've done any studies. I don't know how you would do those studies, because you'd have to do it over a long period of time, and we don't really have a, you know, way to do that. So I'm not aware of any studies, but it would be an interesting thing. I wish we could have gone to the moon for 6 months, you know, to a year. Yes?
There were studies done in the 60s, and some numbers I remember from them about 1/5 or 1/4 of a G.
Okay.
But in the years since, I don't know how much work has been done on that. I know this because Fred Ordway, who was the technical director on 2001, had researched that. Well, he had researched everything. And the centrifuge on the Discovery was supposed to be about 30 meters in diameter. But that wouldn't have, they didn't have a movie studio in England that would fit. So actually the one you see on screen is undersized, but who would know?
Yeah, 1/4 of a G. I don't know. I mean, I don't know what, it seems like you would need more than that, but Yes.
I saw in the movie Plymouth, they used a spin table for that purpose. It was really like, people would be like head to head. And I thought, gee, Coriolis sources would really cause a problem, I would think. But
Yeah, that's another.
I wonder if someone's looked into that.
Yeah.
If it really does have to be.
They have. I don't know in recent years if there's been research. That's.
No, we got to try it over at the Space and Rocket
Well,
Center.
they were supposed to be.
You'd have to have a pretty long arm. I mean, the centrifuge that I trained in was at Brooks Air Force Base, and it was probably about a 50-foot arm or so to get the G profile that we had during launch. So you'd have to have somebody in some sort of environment like that at whatever G you were studying for a long period of time to really understand the effect. Yes?
I really liked on your last slide, you said warp speed would be good, and I think no one would contradict the fact that we need to really start thinking seriously about how we're going to decrease trip times if we're going to get serious about interstellar flight. And NASA ran the breakthrough propulsion program from '96 to 2002, and its mission was to look at breakthrough atomic propulsion schemes, but the funding was cut. What do you think can be done within the NASA administration so that funding can be diverted to these more exploratory deep future propulsion systems?
That's a good question. We're just trying to build a rocket right now. You know, the SLS program, which we at NASA are familiar with, is what all of our resources at NASA are being put on. And unfortunately, we don't have much for science and exploration, things like that. But I do know they are looking at other sources of propulsion. I mean, Franklin Chain Diaz's Vasimer rocket engine is one option, and they are looking at solar electric propulsion and other nuclear, all kinds of things, but that to me is the limiting factor, because chemical propulsion won't work. It's too heavy. So there are things being looked at, but unfortunately there's not a lot of money. I know Les's group at NASA looks at some of those more advanced things. And I don't know, you could probably answer that better than I, how much money we have at NASA to spend on that kind of stuff.
I mean, the Office of Chief Technologist is funding revolutionary research, and the NASA Institute for Advanced Concepts has their call out right now, which will fund low-level research for these kind of things, but there's nothing really specifically like the Breakthrough Physics program that's out there. There is some work being funded, but not focused really on anything ultra-deep space.
I think the most exotic thing I've seen funded flying on Anchor is really antimatter propulsion. I've never seen anything more, more great, more bold, if you like, than traditional physics.
Yes?
Could you tell us about your radiation dose to the cornea? Was it trap radiation or solar? How would you describe it?
Part of it, I had high inclination flights, which meant, I was closer to the poles. And so if you know how the radiation belts go, they're higher at the higher concentration at the poles. So that's probably why, have a higher dose. I don't know the quantity, I don't know the type. Some of it is solar.
No major solar events while you were in orbit?
No, no major solar events. It was from the Earth radiation and just being above the atmosphere. Now, the International Space Station is also high inclination, so, yes.
Hi, you won't remember me, but I was one of the payload flight controllers on one of your missions.
Okay, great.
SLJ. At any time, speaking of the radiation, I know that on some of the missions we worked where we had astronomical instrumentation, we had to safe the instrumentation during the SAA passes, the South Atlantic anomaly. Were you, I can't remember if the SLJ mission passed through the SAA or not. No? Okay, so you have no.
We never had any. We did have some single event upset things with computers on my last mission, my third mission, but it wasn't from the SAA or, anything out of the ordinary. It's just, yes.
Just out of curiosity, with the long-term tracking with radiation effects, are they looking at cognitive decline at all? Because there's a definite link between whole brain irradiation and cognitive decline. I'm just wondering if that's one of the things that they're tracking.
Not that I'm aware of. Maybe they are and I don't know it. But But I do know that, and they call it space dumb. For some reason, when you get up in space, your brain doesn't work as well as it does on the Earth. And that's why you have very extensive checklists. And you know, when I was up there, I would go through each one because for some reason your brain gets a little foggy. And I don't know if that's from radiation or if that's what you're talking about.
Just curious if that was anything that they were tracking.
I would imagine things like dementia and those kinds of long-term Alzheimer's, whatever, they would track that, but so far it's not out of the normal, you know, distribution of problems that people have later in life. Yes?
In the nuclear industry, you use time just shielding for radiation. And is NASA doing anything about electromagnetic shielding?
Yeah, we have shielding.
I'm talking about electromagnetic. It's a newer field which generates a high magnetic field and will actually shield some parts.
Oh, I see what you're saying.
Yeah, I can answer that. There actually has been, the NIAC program funded a phase 1 to look at electromagnetic shielding on the moon. And I'm not sure what came of that for phase 2, but I do know there was some work done on that.
I see what, yeah, I'm not aware of any, but we were shielded from radiation. Most of the shuttle, there were a couple areas we couldn't go that weren't shielded, but that's different than what you're talking about. All right, any other questions? Yes?
You mentioned the health problems that people have when they come back to Earth. Did you see, or were you there long enough or know others, if you stayed there, were there health effects, long-term health effects that you felt while you were in space? Like if you stayed longer, would there be a difference there?
You know, the fact that I lost fluid in my arms and legs, like over a week's period, it's about 7 pounds. And the fact that the fluid, you know, it stays in your trunk area, in your face, that's why most astronauts get puffy. That doesn't really change over long periods of time, so you know that your heart is not having to pump as much, and you know the muscle and bone loss is there. Some of the more longer term effects that I did not experience, but they're noticing now, is how your eye actually changes, the shape of your eye. Now, I was involved with a lot of the experiments where they looked at how well your eye could track and your vision, those kinds of things, which weren't substantially changed over a week or two. But they're finding on the International Space Station that it is a long-term effect, that it does change the shape of your eye and your vision. So that's the only one I'm aware of, other than the ones that I mentioned that are, you know, really long-term, permanent kinds of effects. And if you read the literature, they're doing a lot of studies on the eyes now because they're worried about that effect. Yes?
This will be the last question.
Segueing from there, have they looked into what components of space adaptation syndrome are due to the redistribution of fluids as opposed to simply the input being different from the norm?
The space adaptation sickness is not nearly as big a problem as you might think, because it's any media people here? Let's just say it's exaggerated in the media. About 20 to 30% of the astronauts have some sort of space adaptation sickness, and of those 20 or 30%, very few actually, you know, it becomes a problem where you can't do your job. But even if it is, it only lasts for 2 or 3 days. Yeah. I've not heard of any problem, any cause of that from fluid shift. The cause of it that's been determined is that your eye sees something different than what your body feels, and that conflict, you know, upsets. It's not due to motion.
Okay, so it is entirely due to the sensory input conflict.
I won't say entirely, but that's what I've heard that it's from. I don't know if that's 100%. I'm sure there are other factors. I think fat people do better than skinny people, you know, really. And the really skinny test pilot astronauts had a harder time than the women and, you know, people with more. That's my personal theory. But anyway, it does not cause a problem, because you can take Phenergan or something for motion sickness and it's over in 2 or 3 days. Yeah. You know, so for long term.
We used to have to pad the first couple of days. give
Yeah.
everybody a chance.
Yeah, it's really just a problem for the first couple of days. I didn't have any problems, fortunately. I was very fortunate. I didn't have any. I just felt right at home. And because of that, on my last mission, they wanted me to go deploy a satellite the first day. You know, as soon as we got up there, I deployed a satellite because they knew I wasn't going to get sick. So it just depends on the person. It's nothing you can predict with anything on Earth. You can't predict it by how you do in planes or anything else because it's not motion induced. So, but it's not a problem. It's not a problem for short-term spaceflight or long-term spaceflight. Okay.
Well, thank you very much.
All right.